Friends, can you hear me? Hello.
Yes, sir.
Achha, okay. So let us start with the S parameter what we learned in the last class. So today we'll see some other important results with respect to these S parameters. Okay, and basically what we are going to cover today is very important because when we are performing the measurements of these RF devices, okay, this is somewhat very important to understand where we should perform the measurement, like when we are connecting a cable with a device, correct, and we'll try to measure the S parameter. So we supposed to exclude somehow the characteristic of the cable from the device so that one can find the S parameters only for the device only. It is not like that. That person will be getting the S parameter for the whole system. So we'll discuss these parts also. Okay. Before that, let us quickly summarize all those things what we have, and let us talk about more detail on some matrix property of for this S parameter for some certain conditions. Okay, so what we have seen in our previous classes, that this is the one property that summation n is equal to 1 to capital N S and S and R star is equal 0. Fine. Here S is not equal to R. And other property we have seen that summation n is equal to 1 to capital N S and I star. Okay, this should be 1. So like these two properties, this is actually the properties of a unitary matrix. I believe you know the unitary matrix, which is equivalent to orthogonal for real matrix. Now let us quickly recall what is unitary matrix. Okay, I hope you remember these things, but for your information, I am writing here that if this property is going to be followed, okay, so then we are calling as a unitary matrix. Okay, okay, so this is supposed to be satisfied, correct? Okay, okay, it means that the column of a unitary matrix are the unitary basis. It means what? That each row has the length 1. Correct. Now let us try to prove the S matrix as a unitary matrix. Okay. With certain assumptions definitely. So let us talk over the S matrix as the unitary matrix. Fine. Now the very first thing we can write, okay, if the junction is lossless and all, this is the assumption we made last time, and we got the two very important properties what I just written here. So basis on that, we can write a power conservation law like summation n is equal to 1 to capital N mod of Vn minus square is equal to power. Actually, that is why we are making a square here. N is equal to 1 to capital N mod of Vn plus whole square. This is coming from the power conservation law. Now the same could be further expand as V minus transpose V minus star conjugate is equal to V plus transpose V plus star. Now you must think over here that how I expand like this. Okay, why I'm doing like this, the transpose and the complex conjugate. So for that we require the definition of the average power. What was the definition of the average power? Remember that P average is equal to half of real part of what, that B matrix and I matrix. Correct, it was the thing. Remember these things, remember. But the thing is, like, we are talking about the reciprocal network particularly here. So let us make here T. Okay, it indicates that we are, whatever we are doing here for the reciprocal network. Correct. So you need to take care about this. Is assumption actually. Now if I say the network is not reciprocal, so you need to think, you need to develop a whole new theory. Correct. Fine. Now, so basis on that, okay, one can expand like this. Fine. So these are the assumption, and under these assumption we are working. Correct. In most of the cases, actually, when you do the RF engineering or microwave engineering, you will find that most of the devices, passive devices particularly, they are the reciprocal in nature. Most of the cases, but not for the active devices like amplifier and other things. So that time it is quite challenging to handle those kind of things. Okay, so we will talk time to time all those things. Definitely, we will take some examples as well. Now let us expand further these things. Okay. Okay. Now the thing is this V minus transpose V minus star. The last equation I'm again writing here because we are making a derivation, so we require this thing. So okay, so I'm again writing these things, V plus and star. Okay. Now let us try to connect, okay, these, because these are the voltage wave, incident and reflected. Easily we can convert with the S parameter because we have now a very good background. So what we can write actually, that V minus could be written as, this is V plus, okay, and I think we should write first this things. Matrix S and a column matrix of V plus. Fine. Transpose. Okay, this part I have written like this. Fine. Now this part we can also manage like this. So S matrix and V plus matrix. Overall complex conjugate. Fine. So this is V plus transpose V plus conjugate. Now the thing is, we can see from this equation a little bit rearrangement is required and we will be having a very good result. Correct. So what we can do actually, we can first open it, okay, because we are dealing with the matrices, so please be careful. Okay, this is not a simple linear equations. Okay, so this is T, this is V plus T, then S star, then V plus star. Fine, we can open like this, then V plus transpose V plus star. Now if you are arranging, okay, this equation, so we can write V plus transpose to take common these things, and in curly bracket can be write like this: U minus S star ST, sorry, and S star, and V plus star. Sorry, fine. Can we do these things? Okay, you just brought these things uh, in the left hand side, correct? So you can take common V plus and this thing V plus star. Okay, so this will be this means there will be, if you take it a common out, this will be 1. So like we are dealing with a matrix, so we supposed to write the unit matrix. Okay, so U minus this things, correct? Now the thing is, if you see this equation, okay, so this may hold valid actually if these things like within the bracket, if this thing is 0 or V plus or V plus star is 0, then only the right hand side will be 0. So one fact is clear here, that is that V plus can't be 0 because this is excitation. This is excitation, but mathematically this portion may be 0. Okay, so a possible condition we may obtained here from this equation as, we can write like that: above equation can hold only if, okay, so a condition now we have, which is S transpose S star is equal to U. Fine. And what is this? This is actually the definition of the unitary matrix. Okay, this is what, this is the definition of the unitary matrix, and we can also write down these things as S star is equal to, if you are bringing at the right hand side this matrix, S transpose and inverse. Fine. So this is what, this is what, this T stand for the this things. Okay, so this is actually what the definition of the unitary matrix. Okay, so now uh, like let's say for the two-port network, correct? Let us try to uh, do for the two-port network, and you can verify these things, these facts actually. Okay, and let us try, correct? So for two-port network, a very trivial case we can take and we can see what will happen. So this will be B1, B2, S11, S12, S21, S22, A1, A2. Fine. So two things we have to manage. One is a S star. So if you write S star, this is S11 star, S12 star, S21 star, S22 star, and ST. Okay, this will be S11, S21. Just to inform you here that this thing is a reciprocal only. Okay. Now what we can do actually, ST, S star, and this is supposed to be unit matrix. Correct. Now you can multiply these two. Correct. You can multiply these two, and you will be getting a very important result, which is S11 S11 star plus S21 S21 star. Second element will be S11 S12 star S21 S22 star. Third element would be S12 S11 star S22 S21 star. And this is S12 S12 star S22 and S22 star is equal to unit matrix. What is the unit matrix? Diagonal element will be 1, other will be 0. Okay. So now you can write some conditions here. The first condition is that S11 star plus S21 star is equal to, this is all similar result will be, we will be getting that S11 S S12 star, just a minute, S12 star plus S22 star is equal to 1. Fine, this is one thing. Another thing will be S11 S12 plus S21 S22 star S12 S11 star plus S22 S21 star is equal to 0. What is this? Now if you recall, okay, from this relation, from the property of unitary matrix, we proved the initial our initial statement. Okay, what was, remember these things, this is the thing, correct? So like these results told you about the lossless junction, and that is why we have the power conservation, these things, law actually, and lossless junction particularly. So we written like that incident is equal to the reflected one, and on the basis of that we told this is will be having the unitary property, and the same actually is true. We proved first unitary matrix, and we performed the back reverse engineering, and we got again the same results. Okay, so this proves actually, as per the assumption, as per the initial things what we have taken, and we prove these things again, okay, for the lossless junction, correct? So this is actually the proof, and it is really very useful when we perform some problems actually, particularly when we have the assumption like the lossless junction and all the things, correct? So immediately you can recall this result, and from the unitary matrix, this thing property, you can find it out certain other parameters, correct, or relations. Okay, so this is one thing. Another thing is very important, like I told you that during the measurement, RF measurements actually. So it is really very important that we should know precisely the S parameter of the device. Okay, it is not like that, because when you see the system, the overall system, so it carries so many things, and if you try to find out the individually the S parameter of the device, you're supposed to connect with a machine, and that machine is called the vector network analyzer or network analyzer, by which we can measure the S parameters, correct? So we need to connect these things with the VNA, and the issue is that when you're connecting with the cables, this device to the instrument, So whatever the S parameter you are observing, actually this is with uh, with device as well as cable if you are not perform the calibration. Okay, so calibration I will be not talking about right now because it required the different background. But try to understand that we are not doing the calibration and we will try to measuring the S parameter of the device. Okay, so definitely one should connect with the cables. Okay, and when you are connecting with the cables, it will definitely take the properties of the whole system. It means the S parameter for the cable as well as the device. Now mathematically how we can remove, okay, the cable effects in the net S parameters. Okay, so mathematically we'll try to perform here. Okay, otherwise, like the thing is, if you when you come in a lab, so the thing is, you can see that the calibration we are doing before the measurement, so that where we want to perform the measurement, at that point we are making the calibration. Okay, so we're not talking about much about those things because it require the hands-on. Okay, and right now the condition is not like that, so we'll try to understand from the theory and these things. Okay, so I'm going to talk about the shift in the reference plane. Okay, so let us say we have a N-port network. What is this? This is N-port network. Fine. And let's say we have a number of ports, correct? And we are considering the first port, this is, and the nth port. Okay, we're not making the complex situation. So let's say this is port 1 and this is port N. Okay, now the thing is, just a minute. So making a line, actually, it will clear the facts. Okay, so this point is particularly Z1 is equal 0. This is Z1 is equal L. We connected a cable of length L. Okay, these are the ports of this device, correct? And we connected a cable so that we can connect with the machine. What is the machine? Machine is here, which is called the VNA, vector network analyzer, correct? Fine. So this extra length we need to connect. Fine. Let's say this is Zn is equal 0 and this is Zn is equal L. Okay. Now let us mark the incident and reflected voltages over here. So at this reference point, this is V1 plus and the reflected one is V1 minus. In the same way, if you are talking about at the end of the cable where we are going to connect the VNA, okay, let's make this is V1 dash plus and the reflected one is V1 dash minus. Fine. Similarly, the situation could be realized here. This is incident one, which is a Vn plus, and reflected one is Vn minus. In the same way, at the end of the cable, this could be Vn dash plus, and this is Vn dash minus. Correct. Now we can write certain things here from our previous background. Okay, so at z is equal 0, correct? At z is equal 0 or z1 is equal 0, fine. So we can write v minus is equal to s v plus, fine. And at zn is equal ln, correct? What we can write, or we can write zn, actually it will be quite justified. Zn is equal to means first time we are writing here and another time we are writing here, correct? So this will be Vn dash minus is equal to S dash V dash plus. Okay, fine. Now the thing is, what we need to find it out from the VNA actually. So this second one actually, because ultimately you are going to measure at this point, but you have to reach at this point. Mathematically, we'll try to do here. Okay. So from the transmission line basics, okay, what we can write actually, we can write certain relations because we know the reflection and the incident one, how the equations are there, correct? So we can recall and we can utilize here. The first is Vn plus, we can write Vn dash plus, sorry, is equal to Vn plus exponential j theta n, where theta n is electrical length, okay? Theta n is equal to beta n ln. This is electrical length. And in the same way, we can add Vn minus, okay, Vn minus dash is equal to Vn minus exponential minus j theta n, correct? Now these two things, we know these things, okay, from the transmission line equations. So here, I can explain once again for your information, this is the incident one. So the relation could be related like incident one like this with this electrical length, because anyhow, these things has to cover this L length, and in terms of the electrical length, this is beta L, okay? Now, because the thing is, this is an input system, so it could justify that if we can convert in a matrix form, correct? So let us write down in a matrix form. So there will be a column matrix of V plus is equal to, there will be a diagonal matrix, exponential minus j theta 1, and this will go on up to x exponential minus j theta capital N. This is one thing, and other elements will be 0. And this is V dash plus. Similarly, V minus, you can write down like this, exponential j theta 1, and this is exponential j theta n, 0, 0, and this is V dash minus. Fine. Now what we can do actually, what we can do from the equation, we already have that V minus is equal to S V plus, correct? We have this thing. Now let us utilize, okay, V minus here and V plus here. Fine. Now rewrite these things, okay? When you rewrite this thing, so you can, the equation will be like this, e to the power j theta 1, e to the power j theta 2, and e to the power j theta n. V dash minus is equal to S and e to the power minus j theta 1, e to the power minus j theta 2, like that, e to the power j theta n. And of course V dash plus. Fine. Okay. Now what we can do actually, what we can do, we can rearrange actually. Okay, and the overall we can write V dash minus, okay, and this matrix we are taking at the right hand side, okay. So what we can write, e to the power minus j theta 1, e to the power minus j theta 2, and up so on, it will go on, keeps these things theta up to theta n. Fine. And we have the S matrix. Fine. And then we have this e to the power minus j theta 1, e to the power minus j theta 2, diagonal, only diagonal element will be there, j theta n. Now let's combine these two. Okay, so if you're combining, so it is very clear that this will be, electrical length will be going to add, means it will be minus j2 theta 1. Okay, so better to write like this, S n n, correct, dash, is equal to, because all the element will be like 1 1 2 2 2 3 3 like that. Okay, so e to the power minus j 2 j theta n s and n. It means what actually? It means what? That phase of S and N is shifted by the twice of the electrical length of the shift of the terminal plane N. Correct? You need to move, you need to multiply with e to the power 2j theta n with the original S parameters you will be getting at the end of the cable or near the vector network line, or vice versa. Means you can make the opposite statement as well. Correct. So in this way, now we have a very good tool. Correct. That this could be connected like this. Means the S matrix at the reference plane where Z is equal to 0 and Z is equal L. So both the things is connected only with this exponential term and carries the twice of the electrical length. Fine. Now let us quickly see these things in a two-port network. How the things will be going actually. So for two-port network, what we can write actually, S11 dash, S12 dash, S21 dash, S22 dash is equal to e to the power minus j theta 1 0 0 e to the power minus j theta 2. Then S11, this is the original one. Okay, this is required one, you can say. And all the time from the machine you are getting this matrix. Fine. Now let's rearrange all those things. Correct. Multiply, you have to multiply. So first is this will be keeping as it is. And let us multiply this thing. So this will be S11 e to the power minus j theta 1, S21 e to the power minus j theta 2, S21 e to the power minus j theta 1, S22 e to the power minus j theta 2. Fine. Now again, let's multiply these things. So this will be S11 e to the power minus 2 j theta 1, S12 e to the power minus j theta 1 plus theta 2. Fine. Third term will be S21 e to the power minus j theta 1 plus theta 2. And last one, S22 is e to the power minus j 2 theta 2. Fine. Okay. Now let us make a assumption here that theta 2 is equal 0. However, you are free to choose not to choose 0. I'm just trying to explain that what the result we got. Okay, that is why I'm taking purposefully theta 2 is equal 0. Correct. In that case, okay, in that case, what you can write? Let us write down with some different color. So this will be S11 dash will be equal to S11 e to the power minus j 2 theta 1, and S21 dash will be S21 e to the power minus j theta 1, which is equal to S12 because this is a reciprocal system, and S22 dash is equal to S22. Okay, so like if this is 0, so this will be 0, this will be 0, okay, this will be 0. Okay. So this will be S22 only, correct? This will be S12 e to the power j theta 1. Similarly, S21 g to the power, that is why I have written like this, and S11 is this, correct? Fine. So what you can conclude actually that particularly this term, correct? Particularly this term S11. Okay. So if you want, like, let's say this is your N port network, correct? Okay, let's suppose this is a single port device. Okay, antenna is a single port device, correct? And here you fitted your machine, which is called VNA, vector network analyzer, and this is a DUT. So the thing is, we have to find it out the S parameter at this point, but because we connected with the machine with this L length cable, correct? So we are going to get the S parameter at this reference location. We are telling this thing, this is S dash, correct? Now this L is going to means contributing here, and we have to remove it actually. So the thing is, you will be getting the S parameter like this from the machine. You require S11. So what you will do? That's S11 dash e to the power j 2 theta 1. That's all. So what you need to do? You need to multiply with j 2 theta 1. And what is this thing theta? Theta is beta L. Okay, electrical length. So beta you can find it out from 2 pi by lambda. Okay, and then you multiply. So you will be getting the theta. Correct? Because ultimately the system is going to run at certain frequency. Fine. Or over the large number of frequencies, a band, correct? So we need to perform this exercise, and hence you will be getting your original S parameter of the device. Are you getting these things? So why this is very important? Okay, why this is very important? Because the thing is, like you can relate with your any electronic component, correct? When you're going to purchase for the transistors, correct? So you are checking the certain parameters of the transistors, correct? Ah, different parameter means from the data sheet you are checking all those things, correct? In the same way, when you are going to purchase for the RF devices like filters, couplers, power dividers, okay? So these are the things actually. So definitely there must be some numbers, correct? Like if you're talking about the power division. So like this is the 3 dB power divider, 3 dB power divider actually. Means half of power it is going to divide. Or maybe it is a coupler. 10 dB coupling, 20 dB coupling like that. Okay, so these are the number definitely will be helping you, but at the same time, when you are considering a system, when you are making a system actually, so you require an individual S parameter, correct? So that when you are connecting all the thing in a cascade, so you can manage its mathematics and you can analyze the overall response of the system by these theoretical calculations. So this is the fact actually. That is why this S parameter of the device is needed. In a lab, when you see when we are measuring the from the VNA, so we are making a calibration, and the calibration does the same thing actually. What it does, that it is going to calibrate at this point. It means that these reference location by the calibration we are bringing at this location, correct? So ultimately we are getting the S parameter of the DUT only. Okay, so the thing is from the VNA directly we can measure. Okay, but earlier the things is like it's not like very simple because the calibration method and other things was in a research and